In this video, we're going to use what we learnt in the previous video to calculate the area of an isosceles triangle. Now, in addition to showing how to calculate the area of an isosceles triangle, the main purpose of this video is actually to demonstrate yet another use for Pythagoras' theorem in order to help illustrate both its versatility and usefulness. Now, we know that an isosceles triangle has two equal angles, and we've seen that because of that, it's going to have two sides that are of equal length. So allow me to draw an isosceles triangle here on the whiteboard such that the base of the triangle is the side that is of different length and the other two edges of the triangle are equal in length. So I'm going to draw an isosceles triangle here on the whiteboard. We're going to need quite a lot of space for working, so I'm actually going to draw this quite large on our whiteboard. And then I'm going to grab another layer that I can draw on. Fantastic. So we know our isosceles triangle. We know that these two angles are equal. That's exactly why it's an isosceles triangle. And because they're equal, that means these two edges are equal in length. Now, we're going to be trying to use Pythagoras' theorem to help us calculate the area of this triangle. But Pythagoras' theorem applies to right-angled triangles, and we don't have a right-angled triangle here. We have an isosceles triangle. There's nothing in the nature of an isosceles triangle that guarantees that any of the angles in that triangle are going to be 90 degrees. So how can we get right-angled triangles from an isosceles triangle? Well, because the two sides are of equal length, and because these two sides join the base at equal angles, we actually can prove that the median that runs from this top vertex to the center point of the base, that median line is actually going to join the base at a right angle. Now, we can prove this, but I'm not actually going to get into the proof here, so just trust that it does indeed meet at a right angle. But by constructing that median from this top point down to the center of the base, and because we know that that does meet the base at a right angle, we have now changed our isosceles triangle into two right-angled triangles. And we can label the new edge, the median that we've created, as h, standing for height. So now that we've defined two right-angled triangles from our original isosceles triangle, and we know how to calculate the area of those right-angled triangles from our earlier video on triangles, we saw the area of a right-angled triangle is equal to half AB, where A could be the length of this edge in this case, and B could be our height, or the other way around. It doesn't actually matter, but we know how to calculate the area of a right-angled triangle. So what we need to do is work out the length of this part of the edge and the length of H. Well, if we called the length of the original base, so the entire length of the base C, then we know, because the median line divides this edge in half, we know that each part of this edge, so each half of this edge, is obviously going to be half the length of C, half the total. So it's going to be C over 2. And if we know the length of C, we know the length of the base of the isosceles triangle, we can easily calculate this value. So we've got part of the information we need to calculate the area, but we don't yet have our height. Well, this is where Pythagoras' theorem comes in. We know that given our hypotenuse, L, it's the hypotenuse because it's opposite that right angle, and given the value for C over 2, we can use those to calculate the remaining edge, length of the edge, in our right-angled triangle. So let's write out Pythagoras' theorem. We know is a squared plus b squared equals c squared. How does that apply to this particular triangle? Well, let's say that a is c over 2, so it's going to be c over 2 squared, plus let's say b is h squared, and we know our hypotenuse, of course, is L, so that's equal to L squared. So we can rearrange this to solve for h. So h squared is equal to L squared minus c over 2 squared. Therefore, h is equal to the square root of L squared minus c over 2 squared. So this is going to be an important part of our equation. And we know that the area is equal to, well, what is the area equal to? We know that the area of each of these right angles is equal to half times c over 2 times h. So the area of each right angle is equal to half c over 2 times h. But notice we have two of these right angled triangles. So the area of one of them is half c over 2 times h. The area of both of them is going to be half c over 2 times h multiplied by 2. We have two of them, so hopefully you can see the half here and the 2 are going to cancel each other out, because half times 2 is 1, and 1 multiplied by anything is just whatever we were multiplying it by. So our area of an isosceles triangle is equal to c over 2 times h, where h is equal to the root of L squared minus c over 2 squared. And that's all we need to be able to calculate the area of an isosceles triangle. Now, of course, this may actually be more clearly written as equal to half c h. Both mean the same thing, it's just perhaps a nicer way of writing it, and that's the way that most maths textbooks will actually present that, but it's the exact same formula. So let's now take a look at an example using numbers, and then I'm going to get you to answer an example question on your own. So given an isosceles triangle, and I'm just going to draw a very sketchy triangle here, given an isosceles triangle that has a base of length 6 and two sides of length 5, something like this. So this is 6, this is 5, and this is 5. What is the area of this triangle? So we know that our base has a length of 6. So if we know that the base has a length of 6, that means that c is equal to 6. That means that c over 2 is equal to 6 over 2 is equal to 3. So we've got the length of c over 2, which we know is the length of half of our base, and we know now that we've got the length of L as well. L equals 5, so we just need to calculate h. So h is equal to the square root of L squared, so 5 squared, minus c over 2 squared. C over 2 is 3, so minus 3 squared, which is equal to the root of 25 minus 9, which is equal to the root of 16. So h is equal to 4. So we know that h is equal to 4, we know that c is equal to 6, and we know that our area is equal to half ch. So the area of this triangle is equal to half times c, which is 6, times h, which is 4. So that's going to be equal to half times 6 is 3 times 4, which is equal to 12. So the area of this isosceles triangle, calculated using Pythagoras' theorem, is 12 units. So hopefully that all made sense. Hopefully you followed along with how we took our isosceles triangle, we dropped down a median to turn it into two right-angled triangles. We used Pythagoras' theorem to calculate this height, and then we used our simple area is equal to half AB to calculate the area of one of these guys, but we double it to get the entire area of the triangle. So to test this knowledge out, I'm going to set you guys a question. So I'm going to bring up a new layer, hide out everything else, fantastic, and this is going to be our only question for this video, but it is a little bit of a tricky question. So given an isosceles triangle which has a height of 8 and an area of 48, so the height is equal to 8 and the area is equal to 48, what is the length of side L? So yes, this is a bit tricky because I haven't explicitly shown you how to work it out, but you do have absolutely everything that you need to solve this. So use the equations that I've given you in this video to work out as much information as you can, and you should then see how you can get to the length of side L with just the two pieces of information that I've given you, because it's actually not that hard at all. But if you do get stuck, unpause the video because when we come back I am going to explain exactly how to solve this problem. Okay, welcome back. So firstly, we're only given h and we're only given the area. So what information can we determine using those two values? Well, there's an equation that we saw earlier that relates those two values to the length of c over 2. If you recall, we saw that area is equal to half ch, which can also be written as c over 2 times h. So we can rearrange this because we know the area and we know the height. We can rearrange this to get c over 2. So to rearrange this, I'm going to divide both sides by h. So area divided by height is equal to c over 2. Our area is 48. Our height is 8. That's equal to c over 2. And that's equal to 48 divided by 8 is 6. So we now know that c over 2 is equal to 6. And if we have h and we have c over 2, if we remember, that formed a right-angled triangle with h, c over 2, and the hypotenuse of that was L, which is what we're trying to find. So if we've got h and we've got c over 2, we can now find L, the piece of information we were trying to find, because we know that, well, if this was a squared plus b squared equals c squared, Pythagoras' theorem, we know that c over 2 squared plus h squared is equal to L squared, which means we know that L is equal to the root of c over 2 squared plus h squared. We've just said that c over 2 is 6, so L is equal to the root of 6 squared plus, and in the question we were told that h is 8, so L is equal to the root of 6 squared plus 8 squared. L is equal to the root of 36 plus 64. L is equal to the square root of 100, and we know we're dealing with a length, we're going to take the positive value, therefore L is equal to 10. So you see, it really wasn't that bad. And I wanted to introduce a problem like this because often when we're solving problems, the problem won't necessarily appear in a form that you're used to solving it in. So in those cases where we have a problem, we have some information about a problem, but maybe we don't have a certain piece of information, what I personally like to do is to apply as many formulae and theories as possible that I know to the information that I know in order to see, well, what additional information can I determine? Do I have a formula that relates some unknown piece of information to a series of information that I do know? In this case, we had that formula that gives us, as I scroll up, it would allow us to calculate c over 2 given a and h, which we did know. So do I have some formula that can give me information I don't know using the information I do know? And by finding as much information as possible, you often are then able, eventually, to get to the piece of information that you're actually after. Once you've done that, you can look back and you can see which steps did you take that you needed to take and which formulae did you try applying that actually weren't helpful to get from the initial problem to the solution, and then you can use just the useful parts of that as a workflow in the future to solve that kind of problem, which is especially useful if you want to take the workflow that you applied, say, on paper to a problem and then turn that into a computer program to solve those problems in general. So in conclusion, actually the most important topic that I personally feel was covered in this video wasn't how we calculate the area of an isosceles triangle, but rather how we can apply different theories that we know to various problems in order to gain as much information as possible, in the hope that eventually this will lead us to finding the information that we were after. And personally, I think it's as much an art as it is a science, but I mean, once you get used to thinking in a certain way and thinking in that way, I really find it a fun, challenging and rewarding process, and I hope that you do too. So thanks a lot for watching this video, and I will join you in the next video. Thanks a lot, everyone.